Hi, welcome to the module 0.0. You may wonder why it is called 0.0. This module describes the prerequisites, so only it's called 0.0. Let's proceed. Learning objectives of this module is define the term stress and stress intensity, appreciate the importance of stress in design of machine elements, list the types of stresses and its equations, and also for a given loading condition you need to find what are all the stresses involved. These are all the objectives of this module. Now let us discuss stress and stress intensity. Actually, stress is defined as force of resistance offered by a body against its deformation. Consider you are pulling the member like this. In that case, it is deforming for some time and then it will come to an equilibrium. In that equilibrium position, the applied load and the internal resistance force created is both are equal. So at the equilibrium position, the resistance force generated inside the body is called stress. You may wonder because in your earlier classes you might have seen that stress is prescribed in Newton per meter square or Newton per mm square. But as per our definition, the stress unit is only Newton. The reason behind is, I think you all know the Tamil Augupayar. Augupayar means a word, it actually describes another meaning. For example, some people say, நான் வீட்டில் கேட்டு சொல்றேன். Here, the வீடு refers the people inside the home. But actually, in general meaning, Veedu refers the building. In the same way, whenever you are using the word stress, actually it means stress intensity. Unit of stress intensity is Newton per meter square. So only the this difference. So the stress intensity is defined as force of resistance offered by a body against its deformation in a unit area. So only the unit came Newton per meter square. Assumptions. These are all the assumptions we are considering throughout this module and throughout this subject also. Static equilibrium condition. As I just told, we are considering a member when it is at equilibrium, means the applied force and the internal resistance are unequal. Then the material properties. Material is homogeneous. It means that you are finding the same material everywhere. Isotropic material. It means the material properties are not changing with respect to material direction. In the x direction, in the y direction, in the z direction. If the material properties are same, then it is called isotropic material. So in our case, we are considering isotropic material. And then all the loading conditions are based on Saint-Venant's principle. This may be new to you. Saint-Venant says that whenever you are considering a bar like this, sorry, when you are considering a bar like this, you are applying a force like here. In this case, this material cross section is there now. That cross section dimension, for example, this red color is our member. It is made of square cross section of size A. So the equation what we are going to use to find the stress will be applicable after a dimension here and here. Within this region only our equations are applicable. So we are not considering stresses here and here. That is called Saint-Venant's principle. So we are not considering the material here and here. We are considering only in this region. Next assumption is tensile strength is equal to compressive strength. Actually, for most of the material, this is true, but some material like cast iron, for it tensile strength is lesser than the compressive strength. But for our consideration, we are going to consider both are equal, and then due to this load, some stresses are generated that is within the proportional limit. These are all the assumptions we are considering in this course. Till now we saw stress. Then what is mean by strength? The maximum stress a component can withstand is called strength. Strength is a material property. If you take steel, it is having some prescribed strength. If you are taking aluminium, it is having some prescribed strength. It doesn't depend on the material geometries, but stress depends on material geometry. If you increase the area, stress value will be lesser. If you increase the force, stress value will be higher. But strength is material property. It doesn't depends on any geometry. Next, we'll consider types of stresses. Based on the nature, we can clarify the stress in 5 different ways. First, tensile stress. You are applying a pulling force. In that case, what internally experienced is called tensile stress. If you are applying a pushing force, what we are experiencing is called compressive stress. If the loading is like this, then the stress is called shear stress. If you are bending, means if you are applying a load perpendicular to the length of the bar, then you will experience bending stress. Then torsional stress. Torsional stress means you are fixing at one end and you are twisting in the other end. Then what we are experiencing is called torsional stress. So we will see the formulas for these stresses. For tensile stress, for tensile and compressive stresses, the formula is too simple. Stress intensity equal to applied force by resisting area. So it is, you can say this is load by area. This is the equation to find tensile and compressive stresses. To find the shear stress also, formula is same, except the notation for shear stress. Here shear stress is denoted as tau, and the area which you are going to consider may change for shear stress. And bending stress. This equation you might have derived in your mechanics of solids subject. Here the formula to find the bending stress is my by I. M is bending moment, y is the distance between neutral axis and where we are going to find the stress. That distance may be upper one or lower one. From the neutral axis, the farthest distance, that is called y, and I is area moment of inertia. Based on the cross section, there are various formulas to find the moment of inertia I. Then to find the torsional shear stress, the equation is similar to the bending equation. Tau, torsional shear stress, is equal to Tr by J. T, torsional moment or radius of the cross section, J, polar moment of inertia. Okay, this is the activity which you need to do. For this loading condition, this is a bracket. It is fixed at this portion, and AB is a circular one, BC is a rectangular cross section, and from C there is some projection. You are applying a force Fx equal to 5 Newton in this direction. See here the coordinates are, this is positive x direction, this is positive y direction, this is positive z direction. So Fx is given in positive value. So the force will be in this direction, and Fy equal to also 5 Newton, that will be in this direction. Fz is 0. If this is the case, then you have to say what are all the stresses at A. Say first consider Fx alone. Due to this Fx, the whole member will be pulled. So at A, you may experience tensile stress, and this Fx is, if you are applying directly here, you will experience only tensile, but you are applying with some eccentricity. Due to this eccentricity, this rod may bend in this direction, bend like this. So because of this bending moment at A, you may experience a bending stress also, and due to Fy, you may experience another bending stress in this direction. Due to Fy, you may experience a bending stress in this direction. Next, due to Fy, this rod will try to twist with respect to this point. So, with respect to this point, so you at point A, you may experience a torsional shear also. Like this, you may have to find what are all the stresses involved at a particular point. That is the objective of this one. Thank you.